And yes, I think we are live now. So today I have to apologize because Sabine Heinz, our conductor, is feeling not well. Therefore, she cannot do it, and I have to do her job. I hope you you will forgive me because, of course, I'm not nice as she is, but however, I will do my best. And today we have a Professor Alessandro Bartoloni from La Sapienza of Rome, who will tell you something about the cosmic and sun radiations and the yeah, he will update us about the current technologies and to protect human life and health from the radiation. So we have with us Bernard Foing, the president of Space Renaissance International. Space Renaissance International is the organization that I founded.
Yes, so hello, welcome from Space Renaissance.
Yeah, and
Yeah,
many.
excellent. So,
So okay, Bernard, just give us some information. Thank you very much. Some news.
yeah, okay, excellent. So, welcome from Space Renaissance. Thank you, Adriano. Thank you, Professor Bartoloni, for being here today. Okay, so cosmic radiation, oh, that brings back to my youth, actually, because my PhD was about solar flares and activity, but I have moved in other space topics until now, the Space Renaissance, where indeed we have a number of actions that we have been conducting, that we have agreed at our last General Congress, and that involved very much all the aspect of human expansion into space, some of the technical scientific aspect, like you are going to mention, how to survive in space under radiation, but also some engineering aspect, how do we protect ourselves, how we are going to build the bases in space and on the moon. And also we are looking at more societal aspect, which is how as a community can we bring some universal values when we are going to have a basis in space, values like peace, values like space for all. And in this trend, Adriano has been very vocal and very active in developing our platform Space for All. We have been also Committee for Peaceful Use of Outer Space present there for the first time as an observer. And so there are many things happening on various fronts of Space Renaissance. So thank you very much, Professor Alessandro Bartoloni, to be here with us. And this gives the opportunity to share some information, knowledge, but also remember audience that they can join Space Renaissance as a member, but also some of our activities in committees. And we have been also, we have submitted a number of abstracts for International Astronomical Congress and with high success. So we'll be present at a number of events this year, in particular ISC Milano, where we hope to see many of you. And we'll have also a booth and various activities, Space for All, in addition to our contribution to the technical session. So Space Renaissance is quite active, that you are welcome to join and participate to some of our activities. Then I give back to the floor to Adriano, that is going to read the description of Professor Bartoloni's vita. Thank you very much.
Thank you very much, Bernard. And yeah, of course, we make all of our best wishes to Sabine to recover soon and retake her place in this webinar series that started in 2021, and we are now maybe is the 55th 55 webinar today. However, Alessandro Bartoloni holds an MSc in electronics engineering and began his career in 1992 at the Italian Institute of Nuclear Physics, INFN, working at the Rome Sapienza University Division on developing supercomputers for numerical simulations in theoretical physics. His expertise expanded further during his tenure as a user associate of the European Organization for Nuclear Research, CERN, where he actively contributed to the construction of the compact muon solenoid CMS detector at the Large Hadron Collider LHC. Notably, in 2012, CMS played a pivotal role in the discovery of a new particle consistent with the predicted Higgs boson. Between 1999 and 2011, he served as a lecturer at the Faculty of Engineering at the Sapienza University of Rome, overseeing courses related to computer science. Since 2000, he has been an integral part of the Alpha Magnetic Spectrometer Collaboration, AMS-02, a cutting-edge particle physics detector designed for operation as an external module on the International Space Station. Alessandro's primary area of expertise include cosmic rays physics, space radiation science, and space radiology, radiobiology, reflecting his dedication to advancing our understanding of these critical aspects with the realm of space exploration. So, really great profile, Alessandro. We are very eager to attend your lecture. The floor is yours.
Thank you very much, Adriano. So I will share the screen with the presentation. Just a minute. Let me know if you can see the screen.
Yes, perfect.
Okay, thank you very much for this beautiful presentation. Thank you, Adriano and Bernard, to invite me and to give me the possibility to share the information about radiation in space that since many years is part of my research, especially with the aspect that regards the safeguarding human life and health. As you said, I am Italian Institute for Nuclear Physics in Roma Sapienza Division researcher, and also I'm since many years a user associate at CERN. And instead, since 1 year and a half, I have joined the Moon Village Association recently as a board member. The presentation overview will be essentially the introduction to the components of the space radiation, the different components that let me say, represent this very complex environment. Then I will move to how we are able to measure the space radiation, because methods and technologies to measure space radiation are, of course, crucial for assessing risk and assuring astronaut safety. And the core of the presentation will be instead about the radiobiology, or better, the space radiobiology. That means examining the impact of radiation on living organisms, with particular focus in space from cellular damage to long-term health risk for astronauts. Then I will move to another crucial point about space, that is the space radiation monitoring, or what is usually said dosimetry, because monitor radiation level in space is crucial for assessing, again, the risk and assuring that nothing going bad for the astronauts. And if there will be some time, I also would like to give some concept about space radiation protection that is essentially now rely on passive shielding. I would like to say something about active shielding futures project that will be crucial for shape the next decade of space exploration. So move on to the first part of the presentation about the space radiation components. The space radiation environment is a very complex one, and the main components could be divided by the origin in three main ones. Starting from the one that have origins far from us, we start with the so-called galactic cosmic rays. Galactic cosmic rays are high-energy particles originating from outside the solar system. This is why they are named galactic, because they come from the galaxy, in our case, of course, from the Milky Way, and that, of course, could pose a significant risk to human health during space travel. Then the another components is usually referred as solar energetic particles, but also solar radiation, because it's the radiation that is generated by the sun activity is completely different from the one coming from the galaxy. And the first component, the one that is more close to us, is located in a specific area around the Earth that are produced by essentially the effect of the Earth magnetic field. It is composed by trapped radiation belts, or area in which the radiation coming essentially from the sun is trapped and remain confined inside these regions just around the Earth. So the galactic cosmic rays are essentially energy particles that originate from outside the solar system. In this sketch on the left, you can see that they arise from outside the heliosphere. They essentially reach us not in a straight line like photons, because they are charged particles, so they usually have zigzag trajectory. And when they arrive inside the heliosphere, they are essentially constant. There is no main variation in time. But when they enter in the heliosphere, they are influenced by the solar activity, always referred to as solar wind. And so when they arrive close to the Earth, they are also modulated in the sense that they vary in time. They are not constant. So always present, but not constant, as in fluxes. Of course, the sources of the cosmic rays are astrophysical sources located in the galaxy, like supernova, black holes, and other energy phenomena happening in the universe. This is the typical spectrum. That means how they are essentially present with respect to the energy, because each cosmic ray is essentially a particle. And to this particle is, of course, characterized by its kinetic energy, or the speed at which it travels. And as you can see in this graph, on the left, the less is energetic, the kinetic energy of the particle, and more the flux is high. The flux is, of course, the numbers per unit of time in the unit of area of particle present close to the Earth, or in general in the heliosphere. Energetic particles composed the galactic cosmic ray are completely ionized nuclei. That means they are completely no electrons. They are positive charged, or in case of antimatter, negative charged. They have many orders of magnitude in energy and flux, and you can see so that the whole particle spectrum is a power law in many orders of magnitude. For what regard the composition, the one that most is of concern for space exploration, most are atom nuclei. 87% are around protons with charge equal 1, 12% are helium with charge equal 2, and 1% are instead heavy nuclei. That means atoms that have charge greater than 2. And you can see usually the galactic cosmic ray could be considered primary or secondary. This is very important for astrophysics research, not so important for space exploration, because the difference is that some particle primaries are directly originated by the physical sources, like, for example, protons, helium, carbon, or oxygen, while others are produced during the traveling of the cosmic rays due to the interaction with the so-called interstellar medium. That means the type of media that is inside the two solar systems, two different heliospheres. The heliosphere let me say that are bounded to different stars. In this case, by fragmentation, could be produced many other types of atoms. In this case, you can see lithium, beryllium, and boron. So, for what regard essentially what we have to keep in mind talking about space exploration, their characteristic is that they're always present in the heliosphere. They can vary in flux with solar cycle, but it's like, let me say, like little thin rain. So, in which, as we are in the deep space, we are always immersed in this thin rain. They are not very easy to shield. they are deeply penetrating. And also we have to take in account when we design, we cope with this kind of radiation, that their interaction with shielding or with other type of matter can produce secondary radiation that could be, let me say, risky as well as the primary cosmic ray. So in few words, they are not risky for the short duration mission because, as I said, they are like a thin rain, but for prolonged exposure during long-duration mission, of course, they could increase the risk of health damage. Another component instead is the solar radiation, the second one. This is completely different from the galactic cosmic rays. First of all, because their origin is inside the heliosphere, is the solar activity that will produce this kind of radiation. And the characteristics is exactly the contrary of what is the galactic cosmic ray. It is not always present. It happens for days, like, let me say, a solar storm or like a storm. But when it happens, it's a very energetic event. So it's like a very heavy rain. This is why they could be very, very dangerous. But from the certain point of view, they could be better to, let me say, manage, because if we are able to detect with sufficient advance, it is possible to use some shielding to protect from. For example, the Earth is always shielded by this kind of radiation by the magnetosphere, the magnetic field produced by the Earth, that we can see here in purple in this beautiful picture on the left. The events that produce the space radiation are not unique. There is different kind of events. The two most common are referred as solar flare and coronal mass ejection. The solar flare is a phenomenon that will imply let me say, the involvement of all the solar structure, the photosphere, the chromosphere, and the corona. And during this kind of event, the real point is that there is an emission of electromagnetic radiation that is also produce the acceleration of light particles, like electrons, protons, or in part either ions, that will be accelerated to the near the speed of light, and so they can travel up to the Earth or to the other planets. The coronal mass ejection instead are phenomena that are of the same type with the plasma emitted by the sun, and inside this plasma there is this kind of particle, dangerous particle like electrons and protons, but only they usually are affect the external part of the sun. The reality is that usually the solar flare are coupled with coronal mass ejection, so should happen at the same time. And in fact, usually this kind of radiation is also referred as solar wind, something like a wind emitted by the sun, full of particles and also full of electromagnetic fields that could interfere also, for example, with the satellites that are used for telecommunication, but also can produce stream of very dangerous particles, but I repeat, for limited time. And the third component, instead very close to us, to the Earth, is the one that is, in a sense, originated from the solar wind, because the solar wind, when entered the particles that compose the solar wind, when they enter in touch with the magnetosphere, with the magnetic field produced by the Earth, could be rejected, deviated, or also can be trapped, in the sense that they remain confined inside the line of the magnetic field generated by the Earth. You can see here in this picture that there is some yellow particle that goes around, flip around the magnetic field generated by the Earth. In this case, this is usually some specific area. This area are referred as radiation belts from James Van Allen belts Van Allen belts from James Van Allen, that was the scientist that firstly observed this kind of particle formation space. There is two main areas. Of course, they vary in extension because they depend strongly from the solar activity, but essentially we can define an inner radiation belt that is very close to the Earth's surface at around 1 kilometer height. And of course, they contain medium energy protons and electrons. They are the main particle emitted by the sun. Usually, shielding is effective for this to defend from this kind of radiation. And of course, the inner belt radiation could be a concern for the International Space Station activity that usually orbits around the Earth up to 400 kilometers of height. And of course, for mission that is in Leo, while the outer belt is more distant, 20,000 kilometers from the surface of the Earth, composed essentially by electrons. In this case, there is less, of course, interference with the human activity in space, at least so far. We will see now, later what I mean. Essentially, trapped radiation will provide minimal risk for mission beyond Earth orbit if transition through the Van Allen belt are kept short, because you can also understand from this graph on the right that if you want to go to Moon or to Mars, we have to go through the radiation belt, or we can have to have some particular path flight to reach the deep space that will try to minimize the effect of this kind of radiation. To be, let me say, more talk also to people not so deep in this kind of argument, usually with Leo is something that is referred an area of the outer space very close to the Earth. That means instead the low Earth orbit. The green circle that you can see on the picture is, for example, the orbit in which the International Space Station is. You can see that is inside the inner Van Allen radiation belt. There is other area also referred, especially for satellite orbiting like MEO and GEO. But for our purposes, what is the differences between LEO, for example, the International Space Station, versus BLEO, that stands for beyond Earth orbit? That essentially means all the space missions that are focused to reach the Moon or Mars. And this space exploration in BLEO, that is something that all the National Space Agency has planned in the last 5 years, that could be a concern for what regard the space radiation. The second part of this presentation is about how we can measure the space radiation. And I will use an approach by doing an example, because since many years I was involved in this international collaboration named the AMS, that stands for Alpha Magnetic Spectrometer. That is an instrument that since many years is installed outside the International Space Station. And I took part in the construction when I started more than 20 years ago in 2001. Part of the electronic boards that located on the MS, you can see it on the right of the screen, is a very big object to be in space. Consider that it would be possible to put in orbit only using the space shuttle, and it was done using the last but one space shuttle mission before the retirement of this kind of launch vehicle. And of course, is in international collaboration. It was installed in 2011, May 19. And since then, of course, as any space experiment, is always operating, because essentially cosmic ray arise from the space at any days, any hours. And so essentially there is a control center that is located at CERN, in which time to time, every people joining to the collaboration spend some time to participate to the operation control activity. And the collaboration is a very big one, because the project only for the construction part lasts more than 16 years. And the main institution is MIT, or the spokesperson of the collaboration is MIT, the Massachusetts Institute of Technology, led by the Nobel laureate Sam Ting. But of course, there is a strong support from the NASA Space Agency, and also from the European Space Agency and all the national space agency of the countries that was involved in this collaboration. If you want to know more about this, there is this website, ms02.space, in which there is many information. Of course, if you get the opportunity to visit CERN, the MS Payload Operation Control Center make part of the the site that tourists can visit, because it's considered, of course, fundamental for the activity of CERN, or important experiment. And the only point is that I would like to focus that the original reason to put into space this complex experiment is because it uses the unique environment of space to study the universe and its origin by searching for antimatter, dark matter, while performing precision measurement of cosmic ray composition and flux. And these cosmic rays are exactly the same space radiation that is of concern for space exploration, especially for human space exploration in LEO. The main point, in fact, is that of the three components that I described before, the MS is able to measure all the three: the cosmic ray coming from the galaxy, the one that are emitted by the sun, and the one that are in part trapped, especially the one, of course, in the inner banana belt. And this kind of instrument could be used also to explain something more general. How can I measure the characteristic of the cosmic ray of the space radiation? Since they are composed by particles, starting from very light one electron to very heavy one, like, for example, nuclei of iron, the idea is that we have a multi-instrument device. The kernel is the core, is a magnet, is permanent magnet. This is very important because the cosmic rays are essentially charged particles, and charged particles have the characteristic that when go through a magnetic field, they are, of course, bended. And from this kind of behavior, it is possible to derive many characteristics of the particle. First of all, the sign of the charge, positive or negative, and then many other characteristics, for example, the kinetic energy of each particle. And this is very important also for the possible radiation damages, because the energy associated to a specific particle is essentially the motivation of the damage, is the release of this energy, for example, in the human body, that create possible danger. On the center, you can see a table from which is very easy to understand how this kind of instrument essentially works. In the row, you can see all the different type of instruments that compose the MS. There is no time to go deep to each instrument, but the point is that on the column you can see the different particles, for example, an electron, a proton, an iron nuclei, a positron, an antiproton, an anti-helium nuclei. And you can see that the point is that each particle releases a different signature inside the instrument. So collecting all the information that comes from the different instruments, it is possible to reconstruct. Of course, to reconstruct with an opportunity data analysis which particle has go through the detector and its characteristic, like the energy associated, the charge, which kind of nuclei, and so on. And this is essentially what means that we are able to measure all the cosmic radiation. For example, you can see on the right that all the periodic table is present on the cosmic rays, starting from hydrogen up to the iron and so on. And this measurement could be done for each kind of particle by AMS. Of course, usually these measurements are, let me say, could give us signs about what happens, for example, for open fundamental physics problem like dark matter searches or primordial antimatter searches. But at the same time, this is let me say, the focus of the presentation, that will give us information of the type of damage that we could expect in space. This is a typical measurement of a mass or any instrument doing measurement by space radiation, that is the absolute flux or absolute fluxes. That means to measure how many particles arrives to close to the Earth of each type for unit of time and for unit of measure. You can see here the blue line are the protons and the helium, and the scale here is logarithmic scale, and so that means the protons and helium, as I said before, are the more diffuse particles that compose the space radiation. And another very important measurement that can be done, this is an absolute flux, is instead how the space radiation vary with time. In fact, in this kind of measurement, you can see now on the x-axis, no more the energy of the particle, the spectra, but you can see the time from the installation on the space station of the MS up to the December 2016. And you can see that, for example, the proton, the ion in blue and red, vary with time, the so-called solar modulation. Of course, this happens also at low energy, but this is very important because the low energetic part of the spectra is the one that is more dangerous for example, the human body, for the biological matter. And so these characteristics is crucial to, for example, understand which kind of radiation we will expose in a particular time. This kind of modulation is due to the solar activity. So, going to the core of the presentation, I will now move to the biological effect of space radiation, or what is named space radiobiology. Radiobiology is a science that exists since the beginning of the last century, starting with the Marie Curie, for example, activity in the X-ray, but of course was developed for many different application, especially medical application, which the radiation is used not only for diagnostic, but also for treatment of particular disease, like for example in oncology. And the the first point about space radiobiology is about why we are not concerned about space radiation on the Earth. Why nobody of us is really concerned about this kind of radiation? Because of two main problems. There is an active shielding. We are actively protected by the magnetosphere, that when you see the particles coming from the sun or from the galaxy arrive around the Earth, there is this magnetic field that shields us so that most of the particles are stops or deflected. And this, we have also a passive shielding. This passive shielding is our atmosphere. In fact, our atmosphere like to have a shield of corresponding 10 meters deep, thick water, 1 meter of metal shielding that is constantly protect us. The idea is that when the particle that has not been deflected or stopped by the magnetosphere start to interact with the atmosphere, they start some transformation. It will depend, of course, on the type of particle. There could be different physical phenomena like electromagnetic shower or hadron cascade. But the main point that is important for us is that the particle will transform, and in this transformation, they will release part of the energy. So when they arrive to the Earth's surface, they are less energetic and so less dangerous. In fact, if we take into account the so-called background radiation, that is the radiation that every one of us is exposed every day, only less than 10% depend from the cosmic ray dose corresponding to 0.27 millisievert, while many other components come, for example, from radon, that is especially present as radiation in caves, or from soil, from foods, or from the medical, in the sense where we do some X-man, like, for example, TAC or X-ray. So, at this point, I would like to introduce you another things that is very important, that I think that not everyone could be used to. When we measure the space radiation, we see we are interested to very, let me say, more easy to understand the characteristic, like, for example, the kinetic energy that represent the speed of the particle, the charge, or the atomic number that will represent which kind of particle, electrons, proton, and so on. But when we want to measure instead the damage that this radiation could have on the matter, we talk about dose. And we have different type of dose. That means essentially referring to the energy that the particle will release inside the matter to which they interact with. In the case of when we don't want to distinguish the biological matter or any kind of matter like metal or any other type of material, we call about absorbed dose. And the unit of measure that is used is named Gray, that essentially is joule per kilo. That means the quantity of energy per unit of mass because the idea is that the damage is due to the energy released by the particle or absorbed by the matter that is interacting with the particle. When we want instead to refer specifically to biological matter, and this is the case about radiobiology, we use some different unit, and this comes from the fact that we have to introduce a sort of radiation quality. That means not all radiation act the same. So we introduce a radiation weighting factor that are dimensional factor, so that the unit of measure has the same dimension joule per unit of mass, but the name in this case is sievert, and we talk about equivalent dose. There's the introduction of the biological effect that is not the same if we are considering, for example, an electrons or a protons or a heavy nuclei. This means that not only is the release in energy, but also the type of damage is completely different. And then if we want to make a step further towards the biological effect, and we want to consider in particular the human body, we have to introduce other factors, because of course the human body is a very complex system and the radiation don't behave the same with respect to each different organ. For example, if the organ that we are taking in consideration is the lung, with respect is the brain. And so we introduce many other weighting factors for any specific organ or tissue. We, in this case, talk about effective dose, and the unit is still the sievert. This is so that in the next slide, the gray sieverts are used somewhere. So back to our main point, if on the Earth we have not any concern about cosmic radiation, we understand from the previous description that instead this is not the case on space. In fact, in space there is three main components. None is constant in time. There is many kinds of particles, for proton, helium coming from the galaxy, coming from the sun, trapped in the Van Allen belts. And I will introduce another component that is called secondary radiation or secondary particle, because of course, there is a damage when the radiation impacts on the biological matter, but it could be also some transformation where the radiation impact on the shielding. For example, the metal shielding that we can use to build the International Space Station. And this secondary particle could pose some other risk different from the primary cosmic particle that we have to take in account. You could see here that, for example, the astronaut that is inside the starship is protected by a metal shielding. Of course, that subject may be shielded from the cosmic radiation or from the sun-produced radiation, but it should be impacted by the secondary particle produced by the space radiation in the interaction with the shielding material. It's the same effect that we see, for example, in when we describe the impact of the radiation with the atmosphere. In this case, the atmosphere is the metal shielding. So, generally speaking, human space activity must cope with the high radiation environment of the outer space. Is a real concern for that. But to start to give an idea, which is we are talking about, we'll try to figure out some scenario, especially regarding to the BLEO, or the capability for us to reach the BLEO. And if we consider the exposition, the dose that we expect living on the Earth, what we expect in the ISS is something factor 100 more. In red, you see the multiplication factor. Of course, this is on average and then depend from many different conditions. And to continue and going from LEO to BLEO, on the moon surface, the things are, of course, worse, because the moon is completely outside the protection of the Earth magnetosphere. We see before that the International Space Station is inside the Van Allen belt. That means that the Earth magnetic field is still active, not at the same level of the Earth's surface, but of course is not instead completely, is not more present on the moon surface, in which the expected radiation could be a factor of 300 or 400 more. Going far from Earth, of course, to another very, let me say, destination that could happen in the next decades in the space exploration, the Mars surface. Here the things are going better because, of course, while the moon has atmosphere, there is no atmosphere at all, Mars has an atmosphere and a magnetic field, not at the level of the Earth, but there is something, so that the expected exposition is more similar to the one on the International Space Station. The only point in this case is that the real damage, or the environment that is really more dangerous, is when we travel in this space. Now where we are in the SS, that is inside the protection of the magnetosphere, on the surface of the moon or the Mars. In fact, the factor could be of this position could be really higher and higher. So at the moment, the moon, it seems more reasonable to reach because we are able to reach it in 1 week or 15 days to go and back. While at the moment, for the Mars surface, it's not possible to think nothing that allows us to reach in less than 3 months, or the only to go. Of course, if in the meantime someone has not developed this teleport to Star Trek-like way of transport. In this case, the Mars surface will be for sure more safe than the moon surface. So going back to the effect of the radiation on the biological tissue, we would like to see why there is the limit in carry out space mission due to health effect. In fact, since the very beginning of the energy absorption due to the space radiation impact, of the radiation impact on the human body, that start to happen in seconds, some changes, some biological process or chemical process that create changes in the very low structure, microstructure that compose the human body. That means the membranes, or also the DNA. Since we are exposed to radiation, to the background radiation, the body reacts. There is some mechanism that most of the time, with very high probability, we start a biological process to repair the damages and the changes inducted, created by the radiation. But of course, this biological repair could not always go to the right way, and those, of course, this is also depends on the type of this position. That means how much energy has been absorbed by the body. And so after a minute, this kind of outcome could happen, or something that happens in very short times. It could be time of hours or days or weeks, and this is called usually a deterministic effect that could imply the death of the cells, or even something that is more at the very low level, like mutation, that could be give some outcome here at the distance from this position. So in case of space traveling, also when we are not more in space, and also in the next generation, it will depend if the mutations in the DNA will happen in the somatic cell on their cell. And this is the main mechanism that is ionizing radiation is on DNA. In fact, the particles could have a direct effect. That means that electrons, neutrons, protons directly impact the DNA, producing some break that could be more or less dangerous in the sense that they can be single-strand break or double-strand break. But at the same time, there is another effect that is indirect, in the sense that the radiation interacting with the water present in the body can produce by ionization some particle that then cannot like the particle itself. So a sort of secondary radiation produced by the radiation then go through the human body. And also there is an effect that is specific of some tissues and that is not referred to the real break of the DNA. For example, some effect of this kind could happen on the central nervous system part of the body, like for example in the brain. So this is a typical biological effect. For example, chromosome aberration. After the radiation, you can see here that there is a break in the chromosome due to the radiation. The repair mechanism starts. In a sense, the repair is arrives at the end, the cells, there is no cell death, but the cells is compromised because there is a swap in the chromosome recomposition. This is usually named translocation. It's possible to see, for example, here in this irradiated chromosomic chromosome, there is this swap between these two chromosomes. And another effect that is typical and could be very, very important in space radiation is the so-called radiation quality, what I said before, that corresponds to the fact that the different particle could have different impact. For example, here on the right, you can see the effect of different type of particles, starting from hydrogen or proton up to, you see, increasing the charge, helium, lithium, beryllium, boron, up to the iron. And you can see in these trays that represent the black part represent the damage, that the heavy nuclei could be more dangerous of the, for example, the effect of the hydrogen or the proton. So this kind of particles that are present in space, even if the quantity, the numerosity is less, the protons could be more dangerous and produce some effects that are, of course, more unexpected. Unexpected also because in the clinical field there is not so much experience, because the only particles that are used for diagnosis or treatment are essentially electrons, photons, and protons. So another things that could be very characteristics of space radiation in space radiobiology is the individual radiosensitivity. This appears something strange, but individual radiosensitivity we refer to the different ways in which each person reacts to the ionizing radiation exposure. And in the space exploration scenario, can be, of course, crucial to identify the limits on this feature. This kind of behavior is present in both the deterministic effect, that in the stochastic effect, so the one that happens always a hair of distance from the exposition. Individual radiosensitivity has been reported in experience from the clinical fields, and the origin comes, of course, by genetic susceptibility. That means that every one of us in the DNA repair capability have different, of course, have different efficacy in this kind of process. The International Commission on Radiobiological Protection did in 2007 an estimation that between 5% to 50% of population may be carriers of genetic mutation, conferring more radiosensitivity. And of course, this kind of behavior could be very important and crucial, not only for space radiobiology, but also because it could be of help, for example, in doing precision radiotherapy treatments plan. That means there could be a real synergy between the medical clinical application and the space radiobiology. Also, another effect, typical or in a sense could be characteristic of the space radiation, is the so-called non-target effect. Usually, target effects we refer to what I described before. You can see, for example, in this graph that the radiation impacts the cell or the nucleus of the cell. There is the start after this impact of different biological process. And the outcome could be the cell death or the cell survival with completely repair or with some xenobic instability. The non-target effect, we refer to the fact that there is clinical evidence that there could be some kind of effect, not only that refers to the cell that is affected, that eaten, but also the cell in the standby area. And this especially could be very, very relevant when we cope with the space radiation. That means the heavy ions that are not used, for example, in the clinical field. And so this is another field that is very characteristic about space radiation. So I would like to make a conclusion to this kind of part. And just going through what could be, let me say, a possible characteristic of space radiobiology. And this could be done just answering this question: how many people has flown to space? So up to now, as of February 2024, only 644 people of 44 countries have reached the space altitude according to the Federal the FAA definition that we refer to the fact that in astronomy is a man that is going outside the so-called Karman line that is around 100 kilometers of height. You can see here from this beautiful picture, in between the green and the yellow area. This picture is taken from the International Space Station, the Karman line. And of course, that means that not many people, we have no experience about the behavior of humans with respect to the radiation, especially then if we take in account how many go outside the LEO. For example, only the humans that participated to the Apollo mission. And another interesting thing is that we consider the whole time spent in space totally, but all the more than 600 people is less than 100 years. That means less than one single human being life. So this is why one of the activities that we started by collaborating with the Polyclinic of Sant'Orsola, starting in 2017, this collaboration is to try to increase to advance the space radiobiology knowledge, creating a synergy from people working in the hospital and using radiation since, of course, the last century for treatment and diagnosis, and the expertise of measure the cosmic ray for fundamental physics. We, in this case, make some work on what is called dose-effect relations. That means to study how the exposition to radiation dose will correlate with the biological effect. This is, of course, could be a crucial point to predict the toxicity of space radiation expected for astronauts, space workers, to, in a sense, to create a reliable mathematical model that can describe this kind of correlation between the exposition to ionizing radiation in space and the possible damage to the organ at risk. The idea is to try to, in function of the space exposition scenario dose, that means after defining where we want to go, how long we want to stay, to create the dose through the use of dose-effect model, the space mission risk assessment. Of course, starting from the measurement done by the astroparticle experiment or other experiment in space, we publish an overview about the state of the art, and we identify all the possible effect of radiation that could not only be carcinogenesis, but as you can see, we can impact also different systems, like, for example, the eyes, the central nervous system, and produce some cardiovascular disease. And in doing that, of course, we develop as a first result, as an example of this collaboration, a software that, using the experimental data and the measurement done by the astroparticle experiment, the knowledge developed in the last century about the theory that will describe the behavior of the impact of the radiation on the human body, we will try to create a possible, let me say, as a prediction, the expected damage, for example, in this case, when we use as radiation the one measured by the alpha magnetic spectrometer in the proton spectra. Okay, but back to what is more of interest about this presentation is, let me say, conclude this part, just make notice this report published in January 2022 by NASA. The title is, let me say, very clear: Safe Human Expedition Beyond Low Earth Orbits. Of course, the report is not only about radiation, but it will cover all the aspects that is connected to go in the LEO. But from this kind of table that is extracted from this report and that regard the radiation carcinogenesis risk, is very interesting to see, using the risk described using color code, very easy to understand, low risk, mid risk, high risk, that the point is not where I want to go, but exactly is how long I want to stay. In fact, you can see that there is at the moment a threshold for this kind of risk of 30 days that is low with respect to be mid. Independently, if you want to go to the moon, that is the scenario, the first addressed by the first 4 rows, or to the Mars. And this is, okay, the idea is very, very important for the planet space mission that, let me say, are completely in agreement with this evaluation 30 days. So move to the next part that is about monitoring, because monitoring is, of course, important for space radiation for astronaut safety. And what has been done was, of course, especially done on the International Space Station. International Space Station, as everybody knows, has a science laboratory in low Earth orbit. And its modular design allows experiment to be installed on the ISS and run, for example, in microgravity condition. The ISS radiation protection mechanism is crucial for safeguarding astronauts for the harmful effects of space radiation, rely on physical shielding, passive shielding, water shielding. The point that the altitude of the flying of the orbits of the ISS could be modified with respect to possible space radiation sources, but especially rely on a radiation monitoring system that continuously measures radiation levels inside the station. And this data helps mission control assess the radiation exposure risk to astronauts and take appropriate precautions. In this case, for example, this is what is called dosimetry on board the ISS. There is many different systems. It's my pleasure to show here two systems. One that is essentially a project of ESA and DLR, the German Space Agency, named DOSIS, take this kind of measurement since 2009. You can see here the graphs that are continuously reported. Here on the left, there is the system. Each red box corresponds to a different dosimeter, so a unit able to measure the radiation inside the station. And you can see here, for example, the solar activity. This is very important because those are the radiation that arrives inside the station, of course, is modulated by the solar activity. This is here, the green is the ISS altitude, the International Space Station altitude that is around 350 and 400 kilometers. And here you can see the continuous monitoring of the dose rate. That means the number of grade of radiation per day. Of course, correlated with the solar activity. Essentially, when the solar activity is less, there is more radiation arriving, and vice versa. When the solar activity is maximum, the galactic cosmic rays are less, are more shielded to arrive to us. Another system that was funded by Space Agency, active since 2019, produced by Tor Vergata, another Roman University Tor Vergata, still inside the International Space Station. IMS instead is outside the International Space Station. In this case, you can see that it's possible to make the measurement of the fluxes as well, and also, of course, the doses. But let me say, more important for space exploration and for LEO is the fact that all the National Space Agency are planning to restart the human activity outside the LEO. For example, they are planning to go to the moon or to Mars. So this schedule is taken from the Global Exploration Roadmap, Lunar Surface Exploration Scenario Update 2022. So it's something that describes what is happening now. And okay, traveling to the moon, for example, is something that, of course, is not completely new. And also for the radiation probe, of course, NASA was aware about this fact. In fact, the Apollo 11 mission was in the Apollo 11 mission vehicle was some dosimetry that at the end indicates that the radiation exposure for the whole mission was of roughly 1.8 milligray, which essentially is not so much. For example, you have, for comparison, a chest CT scan typically exposes a person to around 5.8 millisievert. But to be honest, we have to say that when designing the trajectory, for example, through the Van Allen belt, a lot of attention was taken in doing that, so that the flight path could be optimized to not impact, or impact as less as possible in going through the Van Allen belt. You can see in this picture that for response to the Apollo mission in going through the Van Allen belt was designed so that, especially for the outer zone in which the radiation could be higher, there is the minimum impact in going through. But of course, this is something that could be taken in account, especially if we want not if we want to sustain many in the future, in the next years, many space missions starting not once per year, but continuously. For example, in this simulated exposition in going through the Van Allen belt, a so-called worst case, it happens that also 70 millisieverts, so something could be very different. But let me say, the very news is the fact that we, until 2022, we just can rely essentially on the Apollo mission data, while there was a very big success last year because the Artemis mission program produced the first mission, space mission toward the moon, named Artemis 1. It was a success. And even if the mission was with uncrewed, a special crew was on board, and this special crew was on board to measure the radiation to which in the future the real astronaut inside the Orion capsule could be exposed to. In fact, you can see that the Orion capsule of the Artemis 1 was equipped with two phantoms. This was this project, the collaboration between NASA and DLR, named MARE, that means Matrosky Astrorad Radiation Experiment, in which these two phantoms take the position of the astronaut. With the phantom, essentially, in radio biology, refers to a mock-up that was essentially developed to simulate the human body. But the point is that full, in this case, there was more than 6,000 passive detectors, and equipped with that detector around to, of course, take information about the exposition radiation during the traveling. Also, it's very interesting to see that one of the phantom was equipped with a special vest produced by named Astrorad that could be a third prototype of a vest that could be used by the astronaut to protect from space radiation without to have a big impact on the ergonomy, so leaving to the astronaut the capability to operate effectively. And this was also the active dosimeter produced and installed on the Artemis 1. This is the beautiful picture of the vest, and this is the, let me say, the phantoms in the Orion capsule before the start. Of course, this means that things are for real now. We are not only relying on Apollo mission. Of course, people that are involved in this project are now, because the mission ended more than 1 year ago. And they are now, of course, not 1 year ago, roughly 1 year ago, are, of course, evaluating and full information data about this radiation exposure for the going to the moon. To my knowledge, in the Artemis 1 mission, there was, of course, the Van Allen belt going through. There was the flying in the deep space to reach the moon, but there was not any solar storm. As you remember, the solar storm or solar flare is something that happens in a way that is not predictable. For example, this is well known from the Apollo mission, in which a solar storm happens in August 1972, just in between the last two Apollo missions, Apollo 16 that happens in April 1972 and Apollo 17 that happens in December 72. You can see the point of the solar flare is the fact that it lasts only 4 days. It's completely different from the galactic cosmic radiation, always present. But the point is could be very, very dangerous because the particles are real energetic. It's like a real heavy rain or a storm with respect to the thin rain of the galactic cosmic radiation. And again, we are in the near future needs to cope with this kind of problem because the Artemis 2 space mission that is now scheduled for next year, September, for which has been selected a crew, will be the first crewed test flight to the moon since the Apollo. So all the work that has been done for the Artemis 1 space mission will be improved to also manage this kind of event with, for example, the production of radiation crew display or the assessing the shielding option to manage contingency situation, like, for example, a solar flare arriving during the traveling. and especially to enhancing response capability for this kind of solar events. So it's something that is no more about the pole emission, but it's something that is happening in these days. This, for example, is a sensor, a dosimeter that was implemented by NASA, and will be the base that of the dosimeter that will be used to equip the launch vehicle, the Artemis mission, and will allow to monitor continually all the space radiation. Okay, the next step, of course, no date in this case, at least I have no information about that, will be the Artemis 3 mission. In this case, there is a complete change of paradigm, because this kind of mission will see the presence of crewed not only Orion capsule, but also of the human landing system that will give us the possibility to have the man back to the moon surface. In this case, as you say, the mission profiles forecast 20 days, 25 days minimum to 40 days maximum from Orion liftoff to splashdown with, for example, the presence of human for at least 6 days minimum on the lunar surface. So in this case, there should be another improvement for everything that could be done safely. I use this kind of a scenario only to introduce another and final fourth kind of radiation that is very similar to secondary particle. And of course, will happen only in specific location, but it will be the case for the moon. It's named albedo radiation. It is the radiation produced by the impact of the solar energetic particle or the galactic cosmic ray with the regolith. That for a physical process named essentially backscattering produce other particles, essentially neutrons, that could be very, very, let me say, of damage when interacting with, for example, the shield, aluminum shield or polyethylene shield. You can see in this graph on the right different scenarios referring to solar flare or to galactic cosmic rays, and the radiation produced by the backscattering of the primary cosmic radiation or solar energetic particle can produce something that interacting with the shielding could increase up to the 30% the effective dose. So it's something relevant that, for example, for the Artemis transmission or in general for the design of the moon base should be taken in account. The last word about the Mars expedition. Of course, I think that everyone now understood the point, because the exploring Mars will require astronauts to be exposed to galactic cosmic rays in deep space for over a year. At the moment, there is no space transport solution, and more than 19 days spent outside the protection of the Earth's geomagnetic sphere. So in that case, of course, radiation shielding can only moderately decrease the doses. And going through to possible solution, I move to the last issue, that is space radiation protection. Just a few words. Starting from a general principle. What is radiation protection principle of use on the Earth? I usually refer to the ALARA principle, that means as low as reasonable achievable, are based on the fact that I will try, you can see here, this green is the source of the radiation, this is the radiation, and of course that means that I try to limit the time of exposition. Or in case it is possible to increase the C distance from the radiation and extreme adults to use some shielding. But you have to understand that usually this kind of source emit, for example, only protons and at specific energy. So it's monoenergetic and monoisotopic. While this kind of approach is not completely applicable in space, because, for example, if you want to go to Mars, we cannot limit the time more than 6 months or things like that. We cannot increase distance from the galactic cosmic ray, because as said, the galactic cosmic ray is always present as we go in the BLEO. And of course, shielding is not so easy to design, because of course we are not a monoenergetic radiation. We have to protect with different type of radiation, and so the secondary radiation, secondary particle could be an issue. So the ideas at the moment we rely most on passive shielding. Passive shielding is based on the fact that of course the material have different capability to stop the radiation. For example, you can see some different kind of radiation, alpha that essentially are helium, beta are positrons, gamma is photons, neutrons, and different type of course, radiation, different kind of material. In space, the common material used include polyethylene, aluminum, and water. And of course, they are some efficacy. For example, you can see here some measurement done on the International Space Station in which giving the radiation without any protection, it's possible to see that in different scenarios inside the space station, the use of polyethylene will reduce the radiation absorbed of more than 20%. But for the future, especially if we want to go for a long time in this space, maybe we can have to rely on something new, like, for example, active shielding. Active shielding is something that at the moment is not implemented, it's only in research or in ideas. The idea is that we can use exactly like the magnetic field produced by the Earth shield us from the sun radiation. We can try to produce, using electrical cable or cable traversed by electricity, some magnetic field, artificial magnetic field, that protect or create safe zone, safe area in which, of course, the humans or in general can be protected. For example, you can see here a project, a research project in which using electrical cable, put it in this configuration, the magnetic field produced will shield what is inside this part, which, for example, if we imagine that this is the moon surface, or the Mars surface could be the places, the location, the villages, the houses in which live the humans, living instead outside our type of infrastructure. Of course, we are at the moment only at the research level. The same, of course, could be a solution to go into Mars. And this is this picture taken from a research project funded by ESA, in the past named SR2L, in which there is the use of electromagnetic field generation, superconducting magnet. That means magnet that produce electromagnetic field, but using also superconducting cable. It could be a real solution because, of course, superconductor have zero electrical resistance. The only point to make this material works in this condition, they require very, very low temperature, very close to the absolute zero degree, and so cooling system. So the idea is that also research in this kind of material and this kind of technology can be a solution for the future of space exploration, especially if you want to be in LEO for long term. So in conclusion, the space radiation is a complex environment, pluriisotopic, plurienergetics. We have to take care also about secondary particle generation, like, for example, the interaction of radiation with shielding or the albedo radiation on the moon. And especially it's not constant in time and location. For example, LEO is different from Moon or Mars. And the biological effects of space radiation are a major concern for the safety of human exploration. There is some deterministic effect happening just after the exposure, stochastic effect that instead could affect the humans after, many years after the exposition. Of course, another point is that we want to go to the LEO and to stay for a long time. The keywords of the new space exploration era is travel to stay. We want to go to the moon to stay. We want to go to Mars to stay. And one possible solution, the one that we are, of course, spending our research direction, is the dose-effect models, the mathematical models that give us the possibility to predict the effect with respect to the doses expected in different scenarios. Radiation monitoring and protection are, of course, crucial for the safety, and in the coming era, the solar energetic particle events management will be a must, as well as the active shielding will be used to complement the more reliable passive shielding technology used at the moment. Let me conclude with the fact that the knowledge in this field is growing up very fast with the needs, because, of course, all the space agencies have planned to come back to explore. We create a space mission, the LEO, and of course, let me thanks again the organizers who give me the possibility to share this information. Thank you all for your time and attention. Here there are some email address that you can use to reach me, to keep in touch. We are always looking for collaboration. And in this QR code, you can also take a look to the research activity that we are doing at the MS research group in the IMFN Roma Sapienza division. Thanks again.
Thank you very much, Alessandro. This was a terrific lecture, full of information that we learned a lot from this lecture. So thank you very much. And yes, so we are seeing. Okay, so we are back to our conversation. So we have some questions from the audience, and of course we will give priority to these questions, and then I have also some personal questions, but I will wait. So let me take back. So the first one is, okay, I have to say that we have people watching from La Réunion, Ireland, from Serbia, from the USA, from Portugal, and from Italy, and for sure some other countries that are not listed in the chat. However, so the first question from La Réunion, Guy Pignolet would like to hear about radiation at Lagrange points L4 and L5. So I think that my impression is that it's not different from the moon or from the cislunar space. But however, I don't know if there is something particular about radiation in these points.
Oh, let me say that, of course, this is a very hot topic, because the cislunar is, or this kind of L1 or 4 make part of possible solution to improve the efficiency, sustainability, especially for the moon exploration. Of course, from the point of view of radiation, there is not so many difference in the sense that, of course, for what regard the galactic cosmic rays, nothing changes, because they are pointed at anyway inside the atmosphere, sorry, the heliosphere. So in that sense, they are completely equal. And since the galactic cosmic ray, to me, seems the more let me say, crucial thing for deep space exploration, I could say that nothing changed. Of course, there is some optimization with respect, for example, to solar radiation, because if you go far from the sun with respect to the Earth, this means that, of course, there will be less solar radiation. The solar radiation will arrive in a more weak way. Of course, there will be no trapped radiation. But let me say that at the moment, the order of magnitude is the same. There is no real advantages to use this kind of especially, I mean, for human space exploration. This is the point of the presentation. Now, thanks for the question.
Thank you.
To be more accurate, by a factor 2, because when you are on the moon surface, you receive only half of the radiation, not the one which comes from below the surface, but okay, it's a small detail. And in addition, on the moon, you have secondary radiation you don't have when you are in free space.
Yeah.
But yes, it's as dangerous.
Yeah, let me say that the real point is we have to qualify the space mission. Each space mission has its own characteristics, and the real point is that when the future years, not in this decade, there will be a lot of mission, a lot of people around. Of course, we have to try to have more knowledge, to improve the knowledge about the effect of radiation. And in this case, it's not only about doses. This is the point. It's always also about radiation quality. And another point that I would like to stress, because maybe is not so clear, that of course, many aspects at the moment are not so important. For example, the effect on the central nervous system. Instead, for this kind of mission, could be very, very important, because it's not only a point of the effect at the moment. there could be some effect that impact not the health going to the people to the death, but for example, the efficacy of the action. And so the space mission could be compromised, for example, because the astronauts lost their attention or they are not more able to effective pilot the Starship or operate. And this is not only about physics. This is not about energy. It's of course like more about the biological understanding of this kind of effect.
Okay, thank you very much. So we have Dinis Afonso Ribeiro from Portugal. His question is, what kind of secondary radiation is released inside the body due to water inside human tissues? Does the dehydration level affects the resilience to exposure? Who studies this? Are there studies going on this particular aspect?
Oh, I don't know this particular effect. Of course, the point is good because the radiation that is produced by ionization, essentially gamma rays, delta rays, is of course depend from the interaction of the so-called penumbra created by the particle going through the body. And I am no note, but of course could be my thoughts about study of use this kind of effect to improve the radiation. But of course, it makes sense to study. I know, for example, that there is a lot of study on introduce let me say, some torpor, induced torpor in people like in science fiction films, because there is some clinical evidence that this kind of status could imply a major resistance to radiation, especially, and this maybe could also correspond that during induced torpor, there is less hydration of the body. So it could be a side effect of this kind of status.
Thank you very much. Okay, we had another question, but Boris Petrovich said that he already had the answer from one of your slides. And so, okay, Bernard, I think you also have some questions. So
yeah, okay, first, some comments.
It
was also
one for you and one for me, please.
Yeah, it was very nice to hear about your IMS experiment, and I had the pleasure to invite Professor Something at ESTEC, and he gave a beautiful lecture, very inspiring, very motivated, and we had a nice dinner with him and his wife and so on. And so my question about IMS science, which, by the way, if you look at publication for International Space Station, the largest number of publications come from AMS. So that's a great achievement. Not so many publications from life science and astronaut, but a lot from AMS. So my question is, are there some possible follow-up of the science of AMS that is planned for future orbital station, or that we could conduct on the moon?
Okay, at the moment, of my knowledge, there is no any experiment plan to measure cosmic ray for astrophysical studies and investigation like MS primary science mission on the moon. But instead, there is some project. For example, one is named AMS 100 that forecast the presence of a detector in the Lagrange point 1 to choose, for example, the fact that this detector will be very far from the sun, and so will be the information less affected by the Van Allen belts and by the sun radiation. The project at the moment is driven by the Haken people in Germany, Professor Stefan Schall. I don't know how much is the evolution, but there is a lot of information still on the web. The name is MS 100. There is another similar experiment that is named Aladino, but we are still at the same, at the initial stage. the real point is that the next step in this kind of cosmic ray detectors to be thinked for the astrophysical studies, in which, let me say that the most important is to really isolate the galactic cosmic ray. So the real focus is that in MS we have a lot of experience about sun radiation and Van Allen belt radiation because to really understand the galactic cosmic ray component outside the heliosphere, we have to subtract from what we measure. This is why we know all the three, but the real interest for astrophysical sources is the galactic cosmic ray. So in that sense, for astrophysical measurement, the next step seems to be to put a detector similar to MS in the Lagrange point 1, where the sun is far, there is no Van Allen belt, and so this is
the... My question was about cosmic rays and the moon, because we have conducted a study trying to use the moon as a gigantic Cherenkov detector. You know, Cherenkov is what happens when a particle goes at a speed higher than speed of light, and then that creates an avalanche. That's how we detected cosmic rays in the atmosphere. And we could use the regolith of the moon when a very energetic particle, they say 10 to the 20 electron volts, so the most energetic ever, and then this would emit a radio Cherenkov effect.
Cherenkov light, yes. So you can measure the energy and the isotope with the respect
so,
to
and what is the status
of
that? So
of course, this
detector on the moon?
Yeah, this could be a good idea. Let me say that one of the points of this activity that we started in 2017 is always trying to create a synergy between different communities. Because, you know, in the future, we always, for sure, we need the people from different communities talk to one each other. The natural evolution of MS is when MS 100, because this is the let me say, the standard way. But of course, this is another option, especially because it's possible to use the far side of the moon, and so that there will be a lot of opportunity to make a very low noise measurement. And I think that this we require the creation of some synergy. So I think that a discussion could be started, try to put, maybe at the ASC, could be, ISC in my mind, but NAC could be the right place to create last minute special session between astrophysicists, to let people try to discuss from different scientific community, on this project.
So, and then maybe another very simple question on biology and cosmic radiation. Are there now medical counter ways against the effect of radiation? Can we take pill, or are there medicine that could diminish the effect of space radiation?
Yes, I think there is some research since many years about radio resistance. This is also, of course, something that is not only about space radiation. We know that most of the research in the radiation has been done for manage the nuclear plants, for manage, of course, nuclear plant workers, or to manage, let me say, other types of emergency that could derive by not by misuse of this kind of energy. So I'm not an expert about this kind of stuff, but of course there is a research in this kind of direction to try to enhance the radiation resistance using pills or things like that. I don't know at the moment any news about something of permanent, you know what I mean? To manage an emergency, I can use pills, but if I want to live on Mars, I don't know if it makes sense to make pills forever. I don't know. This is, but okay, I'm not an expert about this kind of medicine, but of course, it's a direction.
We had a cosmic study of the International Academy of Astronautics that was led by Professor Susan McKenna-Lawler, where we calculated the effect of radiation to Mars and so on. So we could also advertise. Yes, still a lot of research has to be done on all aspects physical, but also biological. Thank you very much. I'm very informative. And so back to you, Adriano, and for all the questions.
Thank you.
My main question, of course, is more less on the less scientific and more political, philosophical, let me say. So I was really impressed by the synthetic expression you used at a certain point when you say that it's not important how far we are going, but how long we will stay. And this, I think this is exactly the problem, because of course, when we are shifting from exploration requirements to space tourism requirements, to space settlement requirements, living and working in space, then I think the whole dimension of protection from radiation changes. The requirements are quite different, because if we think about living and working in space, and when we are talking about cislunar economy now, so the reality is more advanced than whatever we could predict only a few years ago. So when we talk about cislunar economy, it means that we will have workers on the moon, around the moon, in the cislunar, in the Lagrange points, and so on. And the point will soon be that the only acceptable condition for living in space will be the same terrestrial condition. That is 1G and full protection from radiations. Let me say, in Italy, we have 3 workers dying on their job per day. Each day we have 3 workers dying. So let me say that dying on the job is a normal thing. I don't know the other countries, I know only about Italy, but however, it's a terrible thing. We cannot think that going to space will be even worse than what we have here, that we have to get ill and to have cancer risk and all these kind of things. So it's a controversial discussion, of course, because going to live to the moon inside the lava tubes will resolve the problem of protection, but it will not resolve the problem of gravity. Simulated gravity is not possible in a lava tube. We will have 1/6 of the gravity. My question is very simple. Since you are a researcher in this field, and that's very important for us because we take care of the human conditions. We are a humanist organization. We always start from the needs and the requirements of humans. Okay. Do you have the impression that the space agencies and the scientific community, the scientific space community, is giving the proper priority to this problem of protection from radiations?
Okay, I think that at the moment,
and if not, what should we do to improve the situation? Sorry.
My impression, my perception is that at the moment there is a real long research activity that has to be done in the future. Because you catch the point, we are not talking about astronauts or, in a sense, heroes. We are talking about space workers, space tourists.
Exactly.
The fact that in the future, people not trained, as today, take the airplane to go to, I don't know, from one side to another, they will take and travel in the moon. And to do that, we need, there is a long research activity that has to be done. My impression, of course, is that at the moment, the knowledge is aligned to the planned space mission. This is what I have to say. Of course, this is not for chance. This is due to the fact that the space is, maybe we can say, one of the activity in the world that is more based on a collaborating environment. For example, the exploration, the global exploration schedule for the future is done by the IACG, in which all the space agencies are together to make this planning. So for me, it's not a chance that the actual state of knowledge is aligned to the planned space mission. Of course, that means I expect that in the future will be the same. There will be an acceleration toward this kind of research that take the pace with the planned space mission. Because it is clear that what comes from also the report of the NASA, but that at the moment we have a threshold of 30 days that is completely with the low risk, I mean, is completely aligned with the return of the man on the moon. That is now their time transmission is something that will forecast the stay in space for 25 to maximum 35 days. And so the first answer is I think that has to be done much more than this. But also I have the hope that there will be an acceleration, that we'll have the same the same pace, the same evolution with the planned space mission. What I like of this kind of environment is that, at least to my perception, that is very, let me say, my opinion, the space agency are at all levels still collaborating. I like always to remind us that if there is a place in which people from any kind of nation, countries, are working together, is the International Space Station. Definitely. So space is also an hope that could be drive something new on the Earth. This is, you know what I mean. So, but just going to my stuff, I think that at that moment we are aligned.
It is what Frank White called the overview effect.
Oh, yeah.
You're aware of that, Frank White. The overview effect, that people see the astronauts seeing the Earth from space, understand that there are no borders visible from space, and that we are all together in this small ball in the middle of the universe, and we have to collaborate. And they are not fighting on the ISS, definitely. So this is a good example for everybody, especially in these days. Well, thank you.
Yes.
Thank you very much. And yeah, no, I think it was related to the question by Guy Pignolet in the beginning about L4 and L5, because he is thinking about an on-air infrastructure, a rotating torus or big torus or cylinder, Iceland 1 concept, where a complete ecosystem and Earth-like environment is reproduced in a completely artificial infrastructure, where the rotation can simulate 1G. And the great problem will be protection. And somebody in one of the past webinars mentioned that air can be, and also you said that our atmosphere is equivalent to a 1 meter metal shield. Yes, I took a note here. This is the entire Earth atmosphere.
Yes, we can think.
It is 40 kilometers more or less.
Yes.
But if we have, let's say, an on-air construction with maybe 1 kilometer of air, would be enough to protect or not?
The point is that we have, this is why I think I conclude this presentation, say that the future should be in the direction to use passive shielding and active shielding. Because the main point is that we have an active shielding that is the magnetosphere. The atmosphere makes the rest. But the main point is that most of the radiation is deflected or stopped by the magnetosphere. And the magnetosphere, in a sense, is an active shielding, while the atmosphere is the passive shielding. So I think that the real let me say, step ahead for cislunar, for this space, is to use this to complement these two technologies, active shielding and passive shielding, because only this could be a real make the difference. Let me say.
This could be
at the moment.
Yes.
It's not easy, but I think that okay, I will bet is a strong statement, but I think that the active shielding research is the one that should be pursued and focused more in the future. Maybe also I cited an activity that maybe Bernard knew about the S2 or S2 collaboration that makes some study, investigation in that direction. But anyway, I think that this is the hair should be copied, but taking account this double shielding that we have, the active shielding of the magnetosphere and the passive shielding of the atmosphere.
Excellent. Okay, we have also a last question by Dr. Anahita Nezami. She is interested in superconductor radiation shield idea. Is this currently being tested? What do you envision how it could work to serve as a shield and assembled? So this is related to what we were saying now.
Yes.
Is already some project with some
there is our investigation research project. There is no any real implementation in space, to my knowledge. The real point is that we have to rely on the superconducting technology. That means to use superconducting cables, because the point is that superconducting material behave zero resistance when in the right condition. But the right condition usually means you have to reach the close temperature close to the 0 degree, absolute 0 degree. So this is, let me see, something that work on Earth. Superconducting magnet, for example, the CMS experiment that you mentioned when you read my curricula is based the magnet, the same that is at the center of MS, is in CMS, bigger one, and use superconducting technology. So try to put this kind of technology in space could make the difference also for shielding, not only to measure particles. So this is kind of
yes, and the good news is that electric power in space is abundant and free, and it comes from therefore. Yes, that's interesting also about the problem of the big data, because there is a concern that, okay, I'm going outside of our scope of our discussion today, but there is a concern about the power required by artificial intelligence, the supercomputers and so on, that will cause a 5% increase in a very short time about the energy global demand on Earth. But a good idea would be to put the big servers outside in orbit, maybe. So they will take energy directly from the sun. And the same is for superconductors and to generate shields. I think space is the solution, however, even if it's hard and not.
Yes, ideas out of the box, out of the planet. Yes.
Exactly.
Yeah, actually, we have also an out-of-the-box proposal for shielding. You know, because on the moon, okay, you can go in lava tube, but it's a bit depressive to be always in the dark in the lava tube. So with a team of architects, we propose to build a village in a crater that would be covered by a lake. You know, you would have a structure, and then you have 2 meters of water and ice, and then you could still have a light. And eventually the lake, partly frozen, part of it could be also live. You would have fishes on a gallery above our village. So that's also an out-of-the-box proposal. In having a little city covered with under a lake.
Dear friends, it was a fantastic discussion.
Yes.
Beautiful.
Thank you.
Fantastic discussion. I think maybe it's time to close if we don't
Yeah.
have Other questions? Let me check the chat. No, we don't have other
So,
questions.
yeah, so on behalf of Space Renaissance, I want also to thank you. And okay, let's see also how we can inspire some people on some artificial shading solution, and also putting that together with a technical aspect, scientific, but also all the societal aspect. That is how we enable human expansion into space. So thank you very much, Alessandro and Adriano, for
My pleasure. Thank you to invite me to talk
Back
here.
to you also, Bernard. Bye-bye.
Yeah,
Ad
all the best. Ad Astra.